So, we left off talking about our best density estimate was that we lived in this coasting, not quite critical universe. Well, I said that wasn't the whole story. That's not the whole story because other evidence suggests differently. We now have to put into the equation not just dark matter, but something called dark energy. So, let's go back in the history books, and at the turn of the last century, right, we were just beginning to understand something new about the universe. In the 1990s, we discovered that the universe didn't really look like it was coasting at all. That in fact, the expansion of the universe was not slowing down. The expansion was accelerating. Whoa! How could that be? Because we added up all of the matter. Accelerating, ing. We added up all of the matter, and that said it was slowing down, that we were coasting. But nope. We looked at actual observations. We looked at those galaxies. Remember, galaxies moving away from us, farther they are, faster they are. Turns out that if we look at them, they are moving away from us faster today than they were years and years ago. That the expansion rate is faster today than it used to be in the past. So the rate of expansion is not a constant. Hubble thought it was a constant, that it had always expanded since the Big Bang at the same rate. Nope. The rate of expansion, and I spelled expansion wrong, you put in a little s right there. The rate of expansion was different in the past. It was, in fact, smaller in the past. That means that we are now accelerating faster. Galaxies are getting away from each other faster than they were years and years and years ago. Right? We looked at those galaxies in the past and we said, oh, the expansion rate's like this. But now we look at the galaxies today and we say, oh, the expansion rate is much, much faster. Wow, that is really interesting. How could we possibly explain that? Because we looked at the matter at gravity and that doesn't add up. So we came to this theoretical conclusion that there must be something else out there. There must be a type of energy, because it's not matter, because matter has mass and that has gravity, and so gravity slows it down, not speeds it up. There must be a type of energy that does the opposite of gravity, that instead of pulling things together, pushes on space-time, to make it speed up, to make it accelerate. And of course, we don't know what that energy could be. It doesn't really match with anything that we physically observe, don't see it, therefore we call it dark energy. And guess what, guys? There's not just a little dark energy in the universe. There is a super bunch. We thought that there was a lot of dark matter compared to ordinary matter. Dark energy is a whole huge piece of the pie. So we gotta figure out what is going on here. What do we know? Not much, but we know that gravity should pull things together. That's what gravity does. Keeps us circling around the sun, pulls together, keeps us stuck to Earth. But dark energy has to go the other way. to explain this accelerating expansion. So dark energy pushes apart. So it's opposite of gravity. That's one thing that we know. The other thing that we know, like I said, there's not much. We know what it's not. It is not energy from those sort of normal things that we see. Light. It's not light energy. It's not on the electromagnetic spectrum. It's not a photon. It's not matter. Okay, we said matter and energy are equivalent, E equals mc squared, but this isn't that, right? So we know what it's not. We know what it does. We don't know what it is. Okay, so we don't know what. We know what it's not. We don't know what it is. Another huge mystery here. We are getting into the realm of the mysterious the further we go out into the universe. Turns out, though, that a very smart guy, Mr. Einstein, thought about dark energy, but didn't really know that that's what he was thinking about at the time. When he put together his theory of general relativity, he included something that is known as the cosmological constant. The cosmological constant. So, in his theory, right, when you see a physics theory, it's all a bunch of math equations. Right, not going to show you that. I wouldn't even know where to begin. But we're just going to sort of talk about what it means. So originally, this cosmological constant was a letter, lambda, see that big lambda over there, in his equations. Part of Einstein's theory of general relativity. That's the gravity theory, right, of general relativity that we've already talked about. Okay, so as part of the general relativity theory, the reason that he put it in there is interesting. He actually put the cosmological constant in his theory because he thought the universe had always been the same. Okay, he thought the universe was static. And by that, the scientists at the time thought the universe had always been there, that there was no beginning, there was no end, it didn't change, there was no expansion, none of that. Because this was before Hubble and his redshifts and all the others, LeMaitre and Silver and all the others we talked about. This was before that. And so he looked at his theory and it said, oh, the universe is changing. And he said, oh, no, we don't see the universe changing. I will include a cosmological constant. When he found out the universe was changing, he thought he'd made a mistake. Some people call it his biggest blunder. Not sure if that's really true. So he threw it out. Hubble came along. Universe is expanding, Einstein. It's not static. Oops, Einstein says. Don't need that cosmological constant. But wait a minute. Now, the cosmological constant is a place, a theoretical idea, to represent this new unknown. Now the cosmological constant represents an idea for dark matter, or dark energy, for dark energy. And I'm going to include in the playlist a short video about that Einstein and his biggest blunder. So watch that. It's an interesting story and gives you background here. So now, the cosmological constant represents dark energy because in Einstein's original theory, to keep the universe static, he needed something to counteract gravity. He needed a repulsive force that pushes instead of pulls, okay, that does the opposite, that opposes gravity. And at the time, he put it in so that the universe wouldn't expand, so that it would stay the same. He balanced the expansion with the cosmological constant. Now we put it in and we make it a little bit bigger, and we say that it causes acceleration. So it was Einstein's original idea. It's just now being used a little differently, which is very interesting, I think. Another way to think about this is that the cosmological constant represents vacuum energy. That's another way that we talk about dark energy, is energy of nothingness, okay? Energy of a vacuum. Dark energy, vacuum energy of space. So the cosmological constant is just a piece that we put in the equation that is this unknown dark energy or vacuum energy. And what does it do? Why did I put this crazy graph over here on the side? So this graph is saying time versus size of the universe. We saw this before. Here's our open, here's our closed, our critical, which is our flat, our coasting is the blue line here. Now, what's new about this graph are these numbers over here to the side. They are imagining the cosmological constant. Cosmological constant, here it is, lambda. This says if we have a lambda, if lambda is not 0, right, is not 0, then what do we get? We get accelerating universe, open accelerating universe. If dark energy is 0, we have all these other things. This one is the one that we expected, right? We sort of expected that based on gravity, but galaxies are showing us open. How do we explain it? We add in lambda, we add in dark energy, the cosmological constant. Okay, so clicker, and then watch those interesting videos on Einstein and this whole idea of dark energy. Okay, so what did astronomers have to discover about the universe to bring back that lovely constant?